So, we were talking about panels, right? Plywood, OSB. Is there some sort of composite combination of the two? This is, as I mentioned before. Did you look on the canvas? Is this posted up there? Did you find it? This is D510. D510. APA's literature. I'll look. I forgot to look after class and check. But this is a very good piece of literature. The E330. The E30 is also. That's more general. That covers quite a bit. This has, however, the specific tables for selecting panel. It has two types of tables, I guess. It has the tables that actually give strength. So these are all, and they give it in terms of strength because, of course, you've got a composite. The section is not. What do you call that? So it has a different E modulus in different directions. Every composite, what? Isotropic. Yeah, anisotropic, I guess is what you'd say. It's not isotropic because it has a different E modulus in the different layers as they change. So it makes it very difficult. You can compute it layer by layer, or in the tables, to simplify it, they just give it for the whole thickness, but then they give it in terms of force. Right? So all these tables, instead of being in terms of stress, are in terms of force, and they're they're specific for each width, I guess, or almost each piece. They specify all the different sizes, thicknesses, and you have to pick the one out that matches what you've got. All right. Okay, so that's got that. It also has equations, some very useful equations if you want to try to calculate. Essentially the equations duplicate the tables, but that nonetheless. Okay, that's what that. We've got that, and the. Okay. Forget exactly whether maybe we didn't talk about this. We saw the video of them peeling the logs. Man, I would love to. I've never been to a plant that does that, but that would be something to see, because it seems it happens so fast that the log is just spinning, and to think that there's a blade that's slowly going through it and cutting, because that veneer comes off at an even thickness, and that it doesn't just shatter. You'd think it would just go up in splinters, that it comes off in a sheet. To me is amazing. Whoever discovered that was possible? And they've been doing it for a while, right? This goes back. Plywood was in the I should have looked up the date, 18 something. They started making that, but they had veneer before that. When you think of furniture, veneer on furniture goes pretty far back. It would be interesting to really dig into the history of who first started peeling logs. What an incredible idea. And how you did it without the heavy machinery. Were they doing it by hand? Did they have horses moving these logs around? I can't imagine. Anyway, however they did it. Let's see, however they did it, I don't have my pen working, do I? Oops. Oh, look at this. It's not. It's funny, sometimes this thing retains its settings and sometimes it loses them. I don't know why. It's just a strange thing. And then sometimes it comes up and tells me which monitor, and today it doesn't. And I always guess the wrong one. Okay. That calibrates the laptop. That doesn't do any good. Okay, try number 1. Calibrate. Did it come up? Okay, sorry. Okay, got it. Now we're on. Exit I can't quite see that. Okay, all that. I was just going to make some. Right, and when they peel it off, of course, there are, there are defects, right? And some of those they can patch, and some of them they can't. And defects like the splits that are a little harder to patch, that gets graded. You saw in that video, the sheets come off and they grade them visually. They can see the cracks and they sort them out like that. I think now, well, I know the grading for regular dimension lumber is done with scanners. They scan it. Maybe this is too. I suppose it probably is. They scan it, and that detects the knot holes, and there's an algorithm that grades it. There probably is for this too. Maybe that video is a little bit older. I don't know. But some of these knot holes can be repaired. Some of them, if they're small enough, I mean, you've seen plywood. They don't necessarily fall off. You just have the knot hole in the plywood, right? So that stays in there. I think below an inch or something. There's, you can imagine. And bigger ones, of course, they can either cut them out. You've seen sometimes with, if we looked around, well, this is finer grade. This is all birch plywood, I think. With what do they call it, architectural grade, or where it's got a visual, it's going to be seen. They'll often cut them out, not as a circle, but as a kind of an oval with the grain, and then it blends in a little better. Maybe, I think that's the reason. But then they can punch them out and plug them. Okay, we talked a little bit about that last time, it seems like. So each veneer is a ply. There's a difference between plies and layers. A layer, any that are going, there's I think a slide of this next, but ones that go in the same direction. So if I have them like this, and then, a top and a bottom going in the opposite direction, right? So I'd have two plies here in the middle going the same direction. That would be one layer. That's considered a layer. So there's, you can have something this would be 4 ply but 3 layers. So you have to pay a little bit of attention to that nomenclature, the difference between plies and layers. The face, okay, is obviously the top side, the outermost layer, and the back. The inside, this only has to do, this is with where it gets used as maybe, it's going to be an exterior finish on it, or usually the exterior, it gets painted. It would make a difference as to which one. Or, I take it back. Also with flooring, sometimes they'll plug one side but not plug the other. And of course you want to plug the side if you're going to put carpet on top of it, so it doesn't have holes in it. That's sometimes done. Let's see. Okay, yeah, we saw the video where it gets glued and pressed. Sometimes it's finished sanded. That's part of the, not all of it is, but sometimes it is, depending how it's going to be used. Usually 4x8, but you can get it in other sizes. Right, it's a little bit undersized, 1/8 inch to an 1/8 inch undersized. Right, and thickness you'll see from the tables there's a 32 of an inch. Get rid of this guy here. Okay, here's a thing that explains the plies and layers. So this would be 3 layers and 3 plies. Here's the one I tried to sketch. 3 layers but 4 plies, right? Because these two are going in the same direction. Here we've got 5 layers and 5 plies. Here we've got 5 layers and 6 plies because 2 are going together. So it's just how they lay it up. Sometimes they'll put those inner layers, and that spaces it a little, makes it a little thicker, of course. The strength is coming primarily from the top and bottom layers, and they get, the orientation in the 8-foot direction. So then here are the nominal thicknesses. Yeah, it also has a nominal and actual thicknesses. You can see they're a little bit undersized then, right? 32nd undersize or something like that. Okay. Yeah, we thought we talked about this. Span direction is in the direction of the face grain is going in the 8-foot direction, right? So this is the grain running, whoops, running this way, and it's span. That would be the strong direction, but sometimes you, just from the arrangement of your flooring, you may have some that go in the weak direction, and then the tables give separate value. You have to watch the tables because they'll have strong direction, and then a table next to it says weak direction or something to that effect. So it gives it in both directions, usually. Okay, here's the grading. The grading of these panels is by group. So the strongest is group 1, and the weakest is group 5. This is non-structural, I think, right? Non-structural. This is would get used for something like facing of a wall that's not a structural wall, right? It's just, I don't know where it gets. Well, it's funny. I'm surprised. Poplar is pretty strong wood, I thought. I'm surprised it gets pushed down with, basswood. Okay, that's not that strong, but the real higher strength ones. There's Doug Fir. He's always up at the top. Although he gets downgraded over here. How'd that happen? He's in both. I think the division is here. It's kind of hard to tell, isn't it? But I think it's like this. And yeah, birch plywood is pretty strong. Some of the hardwoods are in there, right? So that you'll see it on the stamp. We'll look in a minute. It'll be by group. So that's what the group is coming from. The higher the group, the stronger it is. Then it also, in addition to the group, it gets a veneer grade, right? And the veneer grade is, you've probably seen these A, B, C, D, and then they'll sometimes have a different grade for front back, so it may be like AC, together like that. And yeah, their A and C are structurally similar. Maybe, I guess that's why they're combined sometimes. So A would be the best, and D would be the worst. It goes in that order. This would be not only strong, but also smooth, paintable, doesn't have any cracks or defects, I think. It's limited to 18 neatly made repairs, however they grade that. Okay, it can be used for boats, sleds. I'm not quite sure what they mean by sleds. What was it? Sleds? Router type. Okay. Okay, and it may be used for a natural finish. So that would be the best grade. Also, the finish, architectural finish on it is good. This one would have a solid surface, but it has more repairs in it. It could have knot holes in it up to 1 inch that have not been plugged, and whatever, yes, other repairs. Oh, synthetic repairs, meaning it's not just plugged with what you've seen that, where it's got this yellow stuff on it. I don't know what that is, but it's like a plastic, I guess, that they'll plug it with sometimes. And yeah, so that's allowed in those because they're not going to be architecturally visible, I guess, or it's not as important. Then you've got C that's plugged and C that's not plugged. So these would be the ones that have holes in them, right? It says it can have knot holes up to 1 inch, but I think it can also have 1.5 inches total width knots and knot holes within limits. Okay, discoloration, limited splits. Okay, tight knots, knots up to knot holes. Okay, so yeah, it can have holes up to 1 inch. Okay, and tight knots, I guess, are ones that don't fall out. knots and knot holes up to, so here you can have a pretty big hole. You could have a 2.5-inch hole, right? That's a pretty big hole in the plywood. So that would be, and they'll mix it, like the DB grade here, or the DC. Oh, here we go. Yeah, A and B could be used on the face, and D and C on the inside. So that would be where the face would be pretty good. But like I say, if you got holes on the inside, then that's not going to be very weather resistant. So they'll also give it a weather rating, and that would, potentially having a hole on the inside, water can get in there and cause problems. So that's usually degrades it. Okay, so right, here's the ratings. That's on this sheet. This is all coming from the this one, the 510. And it can be rated as, this must be like an architectural, I thought was at the top of the list. Sheathing, rated sheathing, exposure 1. So exposure 1, I believe, is the exterior. Exposure waterproof glue, can only be temporarily in water. Okay. Exterior is the one that's actually permanently exposed to weather. So where does that end up? I don't even see that on here. Exterior. Oh yeah, here it is. So that would be the most weatherproof one. This one, marine grade. So they're not really in order here, according to, at least not their exposures. Exposure 1 is better than exposure 2. This has waterproof glue. This only has intermediate glue. You wouldn't think that would be such an issue. Why don't we just use the best glue for all of them? But I guess it is an expense issue, maybe. I don't know why some have different glues. Interior, it's going to be permanently protected, short periods of 90% humidity. Okay, so yeah, and you can read whether they're allowed for OSB or only in plywood. Whoops. How'd I get some jumps? Okay, so here, these are the ones that are OSB, but some of them not, right? Are not available in OSB. So I guess these are the better grades, the more waterproof grades at the bottom. Seems to be divided like that. And right, and of course plywood's available for all of them. And then they have different gradings. These are where you'd see stamped on it AA, AB, AC, something like that. And that usually is it's either front, back, or outside, inside. I'm not quite sure. I kind of forget, but it's one of the, there's a combination of those two grades in them. Okay, so that gives you a little bit, and some of them you can see they specifically say what they're being used for. This is that sturdy floor. That's that specific floor type that uses. I mean, it gets up to L over 480 stiffness, and it uses I-joists, and the rim board has to be made out of LVL, I think, and I mean it's a whole system, and you have to buy into the package. And this plywood would go with that. Plywood or OSB apparently would go with that package. So, and it has to be like tongue and groove and all that stuff to give it that sturdy floor, to make sure it gets that stiffness level. Others, okay, these are sheathing, underlayment, under a, for a layer, floor that's got 2 layers. Okay, so that describes all those. And then the other literature, whoa, look at this. This happened the other day too. Suddenly I get all those marks carry over. I don't know where that's coming from. My thing's going, my tablet. It's going crazy. Okay, this is some more literature. The PS 119. I forgot to bring a copy of that up here, but it has all the tables. It has more. Yeah, this is the original standard, the older one. It is prescriptive, meaning that it has all the forces, and I think it's all by force, like those other tables in the 510. But it gives the strength of all the panels, and and it gives it separately for flexure, shear, bending, and it seems like there was it seems like there was another one. I forget what the other. We'll see. Maybe it'll come up in the slide. Something, and the other one is more prescriptive, and this one I think is only plywood. Oh yeah, it says it's only plywood. This one includes OSB, and what's the other one? The one that's a composite, where you have plies, and then you have the OSB kind of in the middle, or wafer, whatever they call it, board. Okay, so those are the two. So this actually this PS119 is probably the best source of actual data and selection guides for the plywood. The 510 does have a lot of tables in it, and some of them are duplicated. Actually, I should look through. I bet they stole some of these tables out of the 119, but whatever. The 119 also goes through. Both of them go through careful description of all the grading and labeling. So the stamp, you've seen plywood, it gets a stamp on it, and they, let's see if we don't have a slide of that. Yeah, stamps like this, and they, this is a page out of that 119. They go, there's a lot of information on these stamps. So, okay, yeah. Oh, here, AC. That's the back panel versus the face panel. So they're both exterior panels, but that's back and face. So you have the better smooth. You got one side that's paintable, I guess, and the other side that's got maybe some knot holes in it. Wouldn't look quite so good. Then it's also rated. Okay, it's got the thickness on it. Here's the that glue classification. This is exterior. It's graded by the 119. And then there are other things they can have on them where, let's see what else they put on here. I thought there was, here's rated sheathing, siding. Oh, here we go. This is giving the span ratings. So this is roof on center spacing. That's 32 inches on center spacing for the joists. And the other is for floor. So rather than, I mean, I guess they figure a roof must be about 20 PSF, right? A floor, residential, maybe they think 50. Actually, I think it's higher than that, but whatever. They pick, and then they give the on-center spacing for the joists. It would carry that, and it carries it not just in flexure but also deflection. I think they put, we can see in the tables they give different deflection limits, like 360 or 240 or something like that. 180, probably over 180 for the roofs. So it's rated by stiffness as well as for strength, and then that gives it the these span ratings. Okay, there's class 1, whatever that is. So you could read through here. It gives you a lot of detail on what's inside of them. And you can see from these different examples, the stamps they don't always have the same information on them. It depends on what it's really being used for. Like this is a sheathing, undoubtedly, and I would guess exterior, yeah. And so they don't put any span ratings on it. It's not intended to be used as a flooring. It's a vertical sheeting. Okay, here are some others. Right, here's the span rating, roof versus floor. 24 on center, that would be for, I think that's sheathing, sized and spaced, tongue and groove. Number 1 exposure. Oh no, this is sturdy floor. This is flooring. So this is specifically for floor, it looks like. But here you can see this was, this must also be from, oh, this is actually out of the 510. They give you the details of what all of these markings mean, so you can decode it. Okay, and then in terms of starting to specify these guys, this is also from the 510. This is what we looked at earlier, the different groups, and I copied it here because it gets used over, that's what these are. These are the groups, right? So you're choosing a group, or at any rate, here you've got the span rating and the thickness, and you go together and you can see what groups that would be available in. And here, this is specifically for sturdy floor specification over here. So apparently sturdy floor is only using 1 and 4, something like that. And you can see the better grade can be a little thinner. The not so great grade is thicker. So that's the difference, and it runs in that range. Okay, and then you can also, this is then depending on your grade, but this is really how it's being used too, right? I mean, the sheathing with this exposure, architectural 1, which is a better finish, sheathing, sturdy floor here, underlayment, right? So the different grades, but also uses, and then what they're available in terms of, these are all the sizes, these are the way it would be face, back, inner. Oh, okay, so they give all 3 here. So this would be an appearance, these are the better ones. They don't even get up to A, but okay, this would be the appearance grades down here. Okay, so that, and they give you, if you read this description, it tells you in more detail how they're used, right? I mean, it's sheathing, but here it says it directly, unsanded sheathing, grade for wall, roof, or subflooring. Okay, exactly. Applications, engineering design, exposed to weather, moisture, exterior. Okay, so it gives you all the details. So if you're going through trying to specify something, you'd have to look through that in a little more carefully to see which one's really matching up with what your application is. Okay, there is another, oh, I forgot to bring this one up too. And I think I've got a copy of this manual up on Canvas as well. You can look. It seems like I found a PDF of it and I put it up there. It's got, the manual is primarily tables. So these are tables that the American Wood Council provides. And, right, so there's some good tables in that. This has almost more load span tables. It's a whole document that's just tables. It's not, I don't think it's that long, but it has quite a good bit of information in it. So these are some of the tables that are in that Q225. Right, for plywood sheathing, this is your span, right? This is going to be your on-center spacing of the joist. Here's the different span ratings, right? So this would be your roof floor. These are the different, for different deflection ratings, also for bending and shear, and then this should be the strength in pounds per PSF, in PSF. So all these are PSF loads, and you can see some of them are pretty enormous. I mean, wow, 1,000. So you probably wouldn't, I mean, you would never have a specification, I can't imagine, that would be using that. It's just because that deflection limit is so low that it's really designed, I mean, that's a 12-inch spacing, my goodness. So that would be way overkill for that. You do get, some of them you see up in the hundreds. You have to realize we're only talking about a span between the joists, right? It's a very short span. And the load on it, although your floor loading may only be 50 psf, you weigh more than 50 psf, right? And in that small confine, you will definitely get a 200-pound per square foot load. I think that's even the code load is, point loads come out to about 200, as I recall. So, yeah, a lot of these would not be, definitely not be, even though your floor may only be rated as, I don't know, 40 psf, right? If you go with that 40 psf, you're going to feel the bounce probably at I mean, L over 240, I think you almost feel that bounce, don't you? This one's the stiffer one. This used to be the norm for, like, residential floors or live load loading, right? That's where you feel that bounce. So, yeah, you have to be, I mean, this is certainly strong enough, but it might be a little bit bouncy at that 40. Okay. Let's see what else we got. This is one that's out of the manual, and it's similar to those others. This again is comparing the OSB with the plywood, and it's you can see where they draw the line. This must be a very similar table to that other one, where no OSB. These don't meet the OSB, where it usually is the exterior, right, the higher marine grade, and these are the ones that have to be more water resistant, I guess. Right, and some of them are, I mean, I think this is almost the same as that other table we looked at. And the thicknesses they give you in there. Okay, what other tables do we have here? This is out of the 510. Section properties. Okay, here we start to get into, and these are properties that they'll give you the equations. Also in the back of the 510, isn't it? I think they give you all these equations. Somewhere they give them to you. Maybe it's in that PS19. Oh no, here's some. Yeah, in the back of the 510, they'll give you equations to actually calculate bending strength, shear strength, different deflections, bending, weak axis, strong axis. So you can calculate that, and to do it, these are the values that you'd need to input for the different sizes. So given a certain thickness, then this gives you all the information about the weight, the real thickness. Oh no, I'm sorry, nominal thickness. Where's the real thickness? And the area, cross-sectional area, moment of inertia, and so on. And those would be the values that you'd plug into those equations. It also gives you the 510, as I mentioned earlier, has a lot of these charts that are by force, right? These aren't stress, they're well, this one's stiffness, EI. But you can see each of these is something different. This is EI, this is bending, right, flexure. This one is tension. This one is compression. So they're in terms of force, right? Stress times area, stress times area, stress times section modulus. Right, so this would be a moment then, right? This would be inch pounds per foot. Okay, so that would be the moment in inch pounds that it's for this this span rating and number of plies, and it's separated, of course, by the strength. This is the parallel, so this would be the strong direction, and this would be the weak direction, right? Weak direction. Something like that. Okay. And this is, I think, just more. This is EA. This is now the shear, right? Right. Panel rigidity. Oh, you know, what do you call that? Shear rigidity. Rigidity like, oops, I was going to draw it, but like this, right? That kind of rigidity. And panel through shear through this thickness. Oh, okay, yeah, this must be rolling shear in the plane, and this is shear, that other shear, like that. One's like this, and the other's like that. Okay, and then they give you all the equations to plug those into. And it depends, they give you the equations based on single span, 2 span, or 3 span. Okay, usually you're going to be, I mean, it's 8 feet long, for heaven's sakes. Hopefully it spans 3. Right? What would that, yeah, even 24 inches on center would give you 4 spans. So it should be, usually be in that category, but it depends, I guess. And you can see you plug in, this is for the bending strength. So you plug, this is what you got out of the table. You plug this in inches. Yeah, you have to watch the units here. This is in inches. This was in, out of the table was in inch pounds, right? Inch pounds. And of course that's a constant. So you just have to do that, and then you get your result. The result comes out in PSF. So it's you just have to use the units they tell you, and it already has the conversion in it. Okay, this is then for the equations for shear, and these are all in that the back of the 510. And deflection. Okay, and right, so here we've got, right, and the deflection, and that's coming out of the table too. So, okay, so we can try to apply this and see if we can actually calculate one. Here's a roof framing plan, right? It looks like this is the rafter direction, so they're spanning in the strong direction across those rafters. Okay, no snow load, obviously not Michigan. 20 PSF live load, which will give you 28 total with the 8. Okay, so we got that. We're going to look at a live load deflection of 240 and a total for the roof of L/180. Okay, and 24 inches on center. Okay, so what we want to do is choose we want to choose a panel out of all these tables and everything that we looked at. Okay, so it is unsanded. This would be, that one would classify for roof, apparently. Structure 1 sheathing, shear cross gain pound, maximum plywood structural made from group 1 wood. Okay, so this is also shear and cross panel properties are maximum of importance. Okay, so it does have to have the strength. So those two, I think, work. A single floor, it's not a floor. It's not underlayment, right? It's not wall ceiling. No, it's not that. It's not, I don't know, somehow I didn't think it was this either. Sanded grades, high quality surface. No, it doesn't need a high quality surface. It's up on the roof. Superior exterior. No, it's going to be covered. so it shouldn't need that. It's not marine grade. So the ones that look like they apply are these first two, and it says it can be either OSB or veneer, right? So we're open in that, and we've got all these different sizes to choose from. So that kind of is our initial direction we're going. Okay. Now this is from the Q225. The span was 24 inches on center. So this is the roof, right? Is the first one. We don't need anything for the floor. It's not a floor. So that one would do it. That would be kind of like the lowest bottom of the heap, but it would be applicable. Here's my center to center span on that. I am going to use 24 inches. And depending, I guess, on my deflection I want one of those two on different loads. I could choose the loading, and I only had, what I have, 20 was the live load. So the live load, this was the live load. Whoops. So that one checks for the 20. Here's the live load of 20. So that one's okay. And this one was for the total load, right? The total load. And that's certainly, I only had 28, I think, for that, right? 28. So that one's okay. All right, so we make that. Bending. Okay, it says I've got 52. So if I take 52 and put the roof live load CD on that, it actually jumps it up to 65 even PSF, and I've only got 28. So that works. And then for shear, here's shear. It's even higher. Oh, ridiculous. It's not going to fail in shear, evidently. So that's, we only have 28, so that passes. So right now, that would certainly, and that's kind of the lowest grade, right? It's not like I started at the top, but that 24 by 0 would be the bottom of it. So that one looks like it is what we want for span rating. It passes that. What else we got to look for? Oh, the thickness. Yeah, the thickness. Okay, well, we easily made it otherwise, so we could go maybe with the lowest thickness. The bold face ones are what they say predominant. Where does it say that? Predominant are the ones in bold face. So this one would be the most available anyway. 3/8. You can see for sturdy floor, they have separate. They up the demand a little bit there, but we're up on we're not a sturdy roof. We're just going to do a roof here. Okay, so, and now we start looking at the details of how it's going to be set up. Blocking, right? I've got the joists, or the rafters rather, are running like this, right? And if I put a panel on there, that panel's going to run, presumably all the way to the end of one, okay, like that. And this is where you'd have the blocking, right? That's either a free edge, or you're going to have to put blocking on it, right? Blocking, it's either free or the blocking would be another piece of wood you got to nail in there that supports that edge. So you either do that or you don't do that. If you do it, it's somebody's got to go in and nail all those in there. It's a lot more labor, of course. The expense of that wood that's being used for the blocking, plus the time to nail it. So it's not a trivial thing. It does increase the cost of it, certainly, but it strengthens it. So if you can get away without it, I guess you do, but if you In addition to that would be the lumber blocking. I guess you can also use tongue and groove plywood, which does that count as blocking apparently, or panel clips. And panel clips are these. I think they look like you've got the panel and then a clip. I think they look like this. I think they're metal. I should try and get a sample one. They go like that. So you've got your wood here, and then this clip is holding them together. So that's probably another expense, and also the trouble to, I'm not sure exactly how they're held in there somehow. So that's another issue. Okay, so you can see here it's with and without this edge support. And we're using 3/8, 24 with 3/8. That would be this guy, right? And if we go that way, it looks like with edge support we can do 24. Without edge support, we don't make it. So we had 24 inches on center, right? And that looks like it doesn't make it. There's a, look, footnote. Okay, you can also call that 20 inches for 3/8 and 7/16, or 24 if you're up to 5/32. Oh, okay. Well, if you wanted to jump up to keep it at the 24.0 rating, I guess you could jump up to 5/32 and then get away with that. That would give you your 24, right? So I guess that's what I was saying over here somewhere. So you could do that. That would be an option. You could move over, you either have edge support and keep the 3/8. You move up to a 5/32 and you can drop the edge support, or you can drop down to this category, 24/16, and that will, that gives you without edge support. I mean, then you can choose. You don't have to have edge support. So if you're trying, I mean, it's just a economics thing. You can see what the cost of the edge support is going to be versus the cost of the plywood being thicker, and which way is more economic in that regard. Either one would be strong enough. I mean, obviously you pick one that's going to work, but there's some options there. Okay, so once you decide that, then you've got to look at the nailing criteria. Okay, let's see what we've got here. This is floors, subfloors, walls, roof. Okay, this is the one we're looking at for roofs. This is already at 5/16. Okay, if we went with that. 8 penny nails. All the panel edges are 6 inches on center, and the intermediate supports are 12. So I guess these are going to be at the 6, and these are at 12, something like that. And let's see what 4 says down here. 48 inch or greater. Okay, you have to, okay, well, we're not going that. Yeah, you'd have to drop down to 6, but we're not doing that. It's not 48 inches. Okay, so that looks like that would be our nail specification, 6 and 12 with 8 penny nails. Okay. Oh, and they, somewhere they comment, I don't see where that is, but you're supposed to use, this is for thermal expansion. You normally leave a little gap. They're not butted up hard together. You're supposed to leave a little gap for thermal expansion. Okay, and then, what do you want that?
The wood roof system is just one of the reasons the finished building costs are less than those of a comparable steel roof building. Related building features, namely lighter columns, cheaper insulation, simpler connection details, and faster erection, all make this engineered wood roof system the perfect alternative. Installation was fast and simple. Panels were dropped into place and nailed to the top cord of the double lam truss. All plywood seams occur over a structural support. In addition to resisting gravity loads, panelized wood roofs are designed to meet wind uplift requirements and to act as a roof diaphragm to resist lateral forces due to wind or seismic loads. A panelized wood roof system is a model of efficiency. It's possible to install 20,000 square feet in a single day. Wood roofs allow earlier occupancy and quicker turnover of construction capital. This type of system can save a builder 20% over a comparable steel system. Pound for pound, wood is stronger than steel, and wood has much better insulation and acoustical properties than metal or masonry. Wood also provides a warm, aesthetically pleasing effect when left exposed. Another advantage is that lumber and plywood are readily available locally, but lead time for steel can stretch out up to 8 weeks. And bad weather is less of a problem with wood building systems because carpenters can keep working when welders can't. Roofing can be applied directly to this wood deck. No separate layer of rigid insulation board is needed as a base for finished roofing. Wood roof systems like this one are also more dimensionally stable than metal with less expansion and contraction, so the new tenants can look forward to fewer leaks. Here's a look at the finished product. This building is one of 3 in the Midland Plaza complex. These structures range in size from 19,000 to 28,000 square feet. Interior finish work was fast and easy once the tenant layout was determined. Note how the mansard canopy adds architectural continuity to the buildings.
Okay, yeah, it seems like we did we watch that last time? Yeah, we already saw it. I don't know how I got it out of order here. All right, well, you saw it twice. It's not that long. See if I can get it to go away at least. All right, and what else we got here? A little bit of detail on the floor sheathing, different types of floors. So this is, you can see with this is the underlayment, right? Oops, it's going to let me write. This is the underlayment here. And then with a regular flooring on top of it. In this case, if you're putting like carpet on top of it, you'd want a finish that's definitely not with the open holes in it. It would have to be a plugged finish. So that would be a consideration on something like that. This is the sturdy floor arrangement. Although it's funny, they show in this picture regular, looks like regular joists, but I'm pretty certain the sturdy floor requires those I-joists as part of the system. And then, although here they show the I-joists, I don't know, maybe I'm mixed up, but I didn't think that was right. Or maybe they got the diagram mixed up. And this is with the, subflooring, okay, is what they call that, with the floor on top of it. All right, let's see what else we got. Okay, so we talk a little bit more about floors here. This is coming out of, this is the E30, isn't it? Looks like it. That guide, which is also, yeah, here it is. Got the different sections in it. And this is on the flooring. So just a table that gives live loads, right? And this is based on the different, this is your sturdy floor, and this is the other sheathing thicknesses, right? Sheathing, span rated versus thickness. Performance, well, okay, performance category, whatever. The span of each, on-center spacing of the joists, and then the strength, allowable live loads. So that's for picking flooring. You can easily use that table. With the subfloor, gives the nails. Okay, so you can. These are tables that are apparently in the E30. And then this is, okay, a little example of how to actually specify the flooring. So first thing to remember, we looked at this, I think, way at the beginning. There are 3 different spans that they talk about. The on-center spacing span is used for flexure. The inside dimension, right? That would be this one. Clear span is used for shear, and deflection doesn't use either of those. Amazingly, they take the on-center and then they add, depending on the thickness, I think either 2.5 or 6.25, right, to make it a little bit bigger. And those are the spans we'll use. In this example, we'll take a span rated panel, 48 by 24, and 30 seconds, exposure 1, 5 ply. Okay, so we've got all that specified. All right, and then let's see, I think we're after the strength and the deflection, right? Given the sheathing and the deflection limit, I think what we want is the load capacity of it. Okay, so we've got, out of the table, we can get these values, right? This is for, obviously, the bending, the deflection, the moment, and the shear. Okay, and that's going to be that one for the EI, this one for the bending moment, and this is in inch pounds per foot, and this one is in PS pounds per foot. All right, and this is for the shear, so bending and shear. Okay, so we got those three numbers to work with, and we're going to plug those into the equations then. And for flexure, we've got, I guess we're using the 3-span equation, aren't we? Looks like it. 120, no, I use the, oh, here it is, yeah, 3-span equation. That's this one. And this is the value that I got out of the table, right, from the table before. That's that. 1,000, well, that's supposed to be inch pounds. Maybe I should write it. Inch pounds, something like that, per foot. And that comes out then to a PSF is what that results in. This is in PSF, right? So you have to put this in inches and that in from the table. And then you get, wow, okay, 208 PSF. That looks good. The shear, we got 288 using this equation here. And again, the value from the table. And here we've got the EI that came out of the table. And that gives us, yeah, this is a little bit trickier. This gives us the actual deflection for that piece. But we want to know the load that causes that deflection actually. And that you can go L over 3, so you take the limit you want to base that on, L over 360, so this is in inches, so that comes out to that limit in inches, and then you use the ratio of that limit, right, and this, and it gives you the PSF. Okay, how that comes out, I guess you're putting this over, whoops, I'm sorry, this over this, and you solve for that. That's what I think that happens. And it comes out at, then we end up with 190 PSF. Okay, so to get L over 360, you could only put 190 on it, but that's about almost 200 pounds, right? Again, this is like a person standing on it. So you'd get, that would be pretty solid. You easily pass, well, for 200 pounds, if that's the point load, yeah, you'd pass it. Okay, so that one looks pretty good. That would be the load capacity of that panel. And then we've got just a little bit more here. Wall sheathing. All right. This would be the other application. So we looked at roofs. We looked at floors, and this would be the last application would be sheathing. And here it can be placed. You can see this would actually be the strong direction, right? But generally it gets placed like this, vertically, an 8-foot panel on an 8-foot wall. It can be made with, you've seen these, I guess, on cheaper homes primarily, where they just put a little groove in it and it looks like siding, sort of, but it's vertical, and then that gets painted. So that would only be, it would be put up and painted, or you can have a use it as a substrate and then put siding over it, which they show the siding vertically. I don't know. Most siding I know goes horizontally, but okay, either way, whatever. And so those would be those two specifications, I guess. And the only other thing maybe to think about in those terms is, as far as walls, sometimes there is a batten applied, and that provides some water protection. Sometimes it will be tongue and groove like this, like those panels that had the grooves in them that were finished. Those are always tongue and groove, I believe. Or you can get little metal clips. I think they're usually aluminum, I thought, but maybe they are galvanized. And those get placed between the panels. This is to provide some degree of moisture barrier, I think. Okay, that is about all I think we've got on panels. Bang, okay. We got a little bit of time. You want to take an intro look at what we do with some panels? We could do that. Why not? Somehow these lectures all got... I'm doing half and half. It kind of drives me crazy. I don't know about you. But let's see if we can at least start to look at this one. I think this one's not quite so long, so we'll certainly finish this on Thursday. Did it come up? Oh wow, it did. How about that? I can't make it. There we go. Okay. So, a couple other pieces of APA literature here. Hopefully these are also posted. One that's, this is a real nice piece of literature explaining lateral loads and resistance to lateral loads. And it goes through and, I mean, I've taken a lot of the figures out of this for the slides, but it shows how the panels resist the lateral loads, which is kind of nice. And then this is diaphragms and shear walls. This gives more tables, I believe. Doesn't it? Thought it did. Yeah, here toward the back. Gives nailing specifications and some of the more detailed specifications of the use. So these are both APA literature. Yeah, you can see most of this literature is APA, which is the Engineered Wood Association. That's the only, they obviously used to be the American Plywood Association, but then as it expanded well beyond plywood, OSB and everything else, they didn't want to limit their name to American Plywood, So they chose the name Engineered Wood Association, but everybody knew it as APA, so they didn't watch it. So the acronym is APA, but it stands for the Engineered Wood Association. But if you ever, you should go to their website. They have an incredible list of publications. They used to, in fact, years ago, I would contact them and they'd give me, that I could hand out to students, a stack of literature. But now they're kind of reluctant to actually mail that out. They just say, oh, you can get it online. Yeah, you can actually. They've got everything posted online, and it's all free to download, at least the PDFs of it. You can buy hard copies of it, but the discouraging thing about that is it goes out of date every few years. I mean, they do update it. It's pretty regularly updated, their literature. But it's a really great source and for just wood, all sorts of wood products. Okay, including lateral loads here, and this is out of the Intro to Lateral Load Design, I guess, the X305, is that what that is? Yeah, the X305. So we can look at a couple of different types. Vertical, okay, that would be maybe gravity loads coming onto a roof that are going straight in compression through a panel, or the lateral load. Oops, okay, somebody didn't get their pen here. Or what we mean by lateral loads, this would be obviously a wind load, or it could be seismic, wind or seismic. What they've drawn, of course, is wind, and it would be transferred through a diaphragm and then onto a shear panel. So this might be considered the diaphragm. That's supposed to say diaphragm, and this would be the shear wall. So what's resisting you can see this is really I guess you could say it's in flexure, right? If you see it as a very deep beam, maybe it's acting in flexure, but it's certainly picking up that push, and it transfers it to this, but it transfers it to this in terms of shear, right? So the vertical part is really acting in shear. So here we go, the force is applied. Yeah, this is exactly what I just said. There's the diaphragm and here's the shear wall. Or naturally, if the wind changes direction, it switches to the side shear wall, whatever resists it. Seismic forces, here, the ground seismic, and that would almost be, I guess, in the reverse. How's that work? That is moving this way, and the moment of inertia, the inertial resistance is in the weight of the building, wherever you're going to put that, I guess, is acting in the other direction. So that's a little bit more distributed. Okay, and oh shoot! Oh, I meant to bring this model up. I knew I'd forget something today. Well, we'll have to do it. I promise I'll bring it up Thursday. This was demonstrated to me years ago when I was in Stuttgart. I took some engineering courses there, of course, and they demonstrated this. And when I saw it, I thought, "Wow, that's amazing! I'd never seen it demonstrated." But they had a model, and they showed this. I don't have to bring the model. I do have a model that you can play around with, but the concept here, and this is for determining lateral force resistance and how to consider the positioning of shear walls. And there's a rule for it. You've always got to have the shear walls cross at 2 points. So here we've got, right, we've got these and these, so you've got 2 points. And that would be potentially stable. Here you've got no points, right? So this would be 2. Here you've got 0 points. And obviously, if I push on it in this direction, it all just collapses. There is no shear resistance in that direction. Here I've got, they don't connect, but in terms of planes, I do have 2 points. So this one would potentially work. Here, who'd come up with this design? This looks like maybe something Mies would do. They only cross at 1 point. And you'd look at that initially and you might think, oh, well, that should be stable. But they're not. When you push on it, it rotates and collapses. So that's only 1 point. So that's not good. That one's not good. That one's not good. Here, okay, this is very stable. It's got 4 points, so that's excellent. Here, this almost looks like it would be, right? You'd say, okay, we got the 2 shear walls, one in each direction, and here we've got even a third one, but they all intersect at a single point. And again, like this one, with 1 point, they're not stable. They collapse. They rotate about that point. So you've got to have at least 2 points of crossing to prevent that rotation. So that's just conceptually a very fundamental concept or idea to understand about these shear walls. They have to have at least 2 points of crossing. Anyway, so I forgot to bring the model up. We'll do that next time.